In the previous chapter, capacitors were introduced. However, if you've forgotten how they work or what they are, you may want to watch the video reviewing how a capacitor works. So look at the previous video. Up until this point, we've assumed that our capacitors were already charged. We haven't really addressed how they get charged. So let's discuss what happens when we connect a battery to a capacitor. So there's our two flat parallel plates, and then there's our battery being connected to the capacitor. As an analogy, you can think of the battery like an escalator that is transporting the charge from the negative terminal to the positive terminal. So there's work being done by the battery in moving charge from this lower plate to the upper plate. As soon as we insert this battery right between these 2 points A and B, you'll see a very short surge of current as charge flows from the lower plate to the upper plate. If we were to place an ammeter in this circuit in here, we would find that the current would only occur for a very short time interval. The voltage of the capacitor, which I'll label as V with a little c, will increase steadily as charges move from this plate to this plate. So as we build up charge, positive here, positive, negative here, the voltage will increase as more charge is accumulated on each plate. And as more positive charge accumulates on this top plate, the new positive charges that come up here will feel even a greater repulsive force acting on them. The charge on these plates will eventually get so large that there will be no more new charge that can arrive. And we can say at this point the capacitor has been fully charged. So this would have a final charge positive Q, and this will have an equal charge but is negative Q. And at this point, the voltage of the capacitor will be equivalent to the voltage of the battery. Now let's consider an RC circuit shown here. It's called an RC circuit because we have a resistor and a capacitor. So any circuit that involves resistors and capacitors are called RC circuits. At t equals 0, the switch is thrown and closed. And now that there's a complete circuit that can form, current will flow away from this battery I, and then up through here, and then continuing on all the way around through this circuit in this fashion. Initially, the capacitor will be uncharged, so its initial charge Q at time 0 will be 0 coulombs. Now this is important. An uncharged capacitor will provide no resistance to the charge flowing on or off these plates. So at t equals 0, the capacitor is uncharged, and instantly it provides a 0 resistance to the current. So basically this capacitor will act like a wire. So you could just imagine as a wire going straight through here. So when the capacitor is uncharged, it behaves like a piece of wire with 0 resistance. Now let's apply Kirchhoff's loop rule, and let's add all the voltages around one entire loop. Let's start here and go around the loop this way. Kirchhoff's loop rule says the sum of all the voltages will add up to 0. So let's go over here. We start here and we go over the battery and go from the negative terminal to the positive terminal. So we're going upstream here. So this is going to be a positive EMF. And then we go off across this capacitor. So let's say that it did have a voltage across it. So we'll have a voltage VC. The reason why I'm using a negative here is because as this thing becomes charged, this plate over here will become positively charged, and the other plate, which is connected to the negative terminal here, will become negatively charged. So now I'm going across the capacitor from the positive to negative, so I'll drop by this voltage of the capacitor VC. And then lastly, as I go along this part of the resistor in the direction of the current, I'll lose a voltage equivalent to I times R. And then I'll get back to my starting point, and so this all adds up to 0. Rearranging for the EMF, we find the EMF is equivalent to the voltage drop over the resistor IR plus the voltage across the capacitor. We also know that the capacitance is equal to the amount of charge on the capacitor divided by the voltage across that capacitor. So let's substitute that into this expression. So that EMF is now going to be equal to IR plus the charge divided by the capacitance. If I'm going to rearrange that for voltage of the capacitor, it will be Q over C. Now, at time t equals 0, the capacitor is initially uncharged. So this means that this is 0, and so we end up with the EMF of the battery is equivalent to the voltage drop across just the resistor. Now, as time passes on, we'll find a couple things happen. The capacitor will start to get charged up, and so you'll start to develop positive Q and negative Q on each plate. And eventually the capacitor will become fully charged and can't accommodate any extra charge. And at this point, when the capacitor is fully charged, no more current can flow on or off these plates. So at a long time afterwards, so at t equals infinity, the capacitor behaves as a basically infinite resistance, like an open circuit. So you can imagine this capacitor is now being like an open switch here, and so that no current can flow on or off this capacitor. So when the capacitor becomes fully charged, you can imagine this wire has basically been cut open, and so you can't get current that flows on or off of that capacitor. So now Q at infinity will be equal to the maximum amount of charge that you can get. The current that flows through the circuit will now be 0. And now using this equation, the EMF is equal to IR plus the voltage of the capacitor. We'll see that the current is 0 now, and so the EMF is equal to the voltage of the capacitor. So the voltage of the battery will eventually be equivalent to the voltage of the capacitor, which is equivalent to the amount of charge on the capacitor plates divided by the capacitance. Here's an animation to show you what is happening graphically to the charge and to the current for this RC circuit. So we have a battery with a voltage of 10 volts, capacitor of 2 microfarads, and a resistance of 1 mega ohm. And then watch as I throw this switch. I start off with a 0 charge, but I start off with a maximum current I. And as time progresses, eventually you'll find that the capacitor will become fully charged to a value of 20 microcoulombs, and the current will die out to be 0. This value here, we're not going to get concerned with this. This is more with physics C. This is called the time constant. Usually about 5 time constants. So 5 of these, you'll eventually reach a steady state. You'll be within 1% of 0 here and 1% of the total maximum charge. And so we'll say roughly you're at the right point for steady state conditions. By the way, there is another graph I could have plotted as well, which would be the voltage of the capacitor, and it would be the same pattern as the charge. So if you replace this with V of the capacitor, we'd start off with an initial voltage of 0, and then eventually it will reach the total voltage of the EMF, which is 10 volts. And you'll notice that these are exponential functions. So what happens if we discharge a capacitor? So let's suppose we take that capacitor that we charged earlier with a charge Q and a voltage Vc across this capacitor, and we connect it just simply to a resistor and a switch. At this point, there is no current going through the resistor because the switch is open. So we then throw the switch and close it, and hopefully you can tell now that the current will actually flow in the opposite direction now. And the reason why now is because this has been charged positively now from when it was connected to the battery. And so the current will flow in this direction now, opposite that it was in the earlier circuit. This capacitor essentially acts like a potential difference or a battery. So let's apply Kirchhoff's loop rule in this fashion. As we go across this capacitor, we'll have a gain of voltage Vc. Then as we go over here across this resistor here, in the direction of the current will have a loss of the voltage across the resistor, and this will all add up to 0. So rearranging for the current, we'll get the voltage of the capacitor divided by the resistance is equivalent to the total current. After a long time, the capacitor will eventually discharge and have no more voltage across it, and hence the current in the circuit will eventually be 0. Suppose we could say at t equals 0, the voltage of the capacitor is the initial voltage, V0. And you recall that capacitance is charge over voltage, so the initial charge on the capacitor will be equal to the capacitance times the voltage of the capacitor. So at t equals 0, the initial charge of the capacitor is really equal to the capacitance times the initial voltage, V0. Okay, so what happens after a long time? At t equals infinity, well, more and more charge leave this positive plate and go to the negative plate. Eventually you get to a point where it becomes fully discharged. And so the charge on the plates at infinity will be equal to 0. Now, because charge equals capacitance times voltage, as this approaches 0, so will the voltage of the capacitor. So the voltage of the capacitor will eventually die out to be 0. And because the current in the circuit is equal to the voltage of the capacitor divided by the resistance, and we see that as the charge goes to 0, the voltage goes to 0, and because the voltage of the capacitor is 0, now there won't be any current left in the circuit, so everything dies out to 0. So let's examine this graphically now. So here we have a fully charged capacitor with a voltage of 10 volts and our resistor of 1 mega ohm, and our capacitance has a capacitance of 2 microfarads. So let's throw the switch and observe what happens. There's the capacitor fully charged glowing to 0. There's the initial current at a maximum value and also dying out to 0. Eventually, after you reach about 5 time constants, you'll reach a 0 current and a 0 charge. And there are the graphs included in the notes as well. We can also show a voltage over time graph as well. And there's the initial voltage of the capacitor dying out to eventually 0. The reason I put the current below the axis is simply because the current was going the opposite direction than it was in the previous part. So you could have put the curve up in the above part, it really doesn't matter. Okay, and that's our discussion of charging and discharging capacitors in RC circuits.